Through this project, we aim to explore the various methods of energy conversion and storage mechanisms available. Depending upon their nature behind, we can classify the mechanisms into 4 main types: solar, mechanical, thermal, and multi-based. Coming to the photovoltaic-based systems, here the light is converted into electric power, leaving no net chemical change behind. Photons with energy greater than that of the band gap generate electron-hole pairs, which are then separated by electric field present in the space charge layer. The negative charge carriers move through the bulk of the semiconductor and the holes drive through the external circuit. The positive holes are then driven to the surface where they are used to oxidize the molecule, which further reduces itself to generate an electron which re-enters the bulk of the cell from the external circuit. Then we explored different configurations possible in a photovoltaic system and also studied the factors due to which the overall efficiency of a solar cell is affected, which include the photocurrent, photovoltage, and fill factor. Based upon the nature of the active layer present between the photovoltaic cell, we can classify them into perovskite and organic-based solar cells. Due to their different natures, though the mechanism followed is quite same by both the cells, their reaction to it is different, as in an organic solar cell, an exciton is produced. These cells have proved to be groundbreaking due to their high power conversion efficiency.
Second type of energy conversion based on solar energy is through photocatalytic cells. This energy conversion and storage units are connected via an electrolytic medium. Redox reactions will be involved during the energy storage, that is in photocharging. Now, during discharging, process of counterbalance takes place. Means charges will come back to the oppositely charged electrode from the energy storage unit, and cations and anions in electrolyte will provide counterbalance. Depending upon the electrodes available for the charging system, the photocatalytic charging systems can be divided into 2, 3 or 4 electrode configurations. The low solar conversion efficiency is a disadvantage which requires much effort to achieve the threshold of commercial application.
Mechanical energy storage system. In this system, there is a conversion of energy from mechanical to electrical form. In times of low electricity demand, the electrical energy is taken from the grid and stored in the mechanical form. And when the demand is high, the energy is then converted back to electrical energy and transmitted back to the grid. This system is classified into 3 types: pumped hydro storage system, flywheel energy storage system, and compressed air energy storage system. Pumped hydroelectric storage system. In this system, large amount of water is delivered to an upper reservoir during the period of excess generation, and it is converted back to electricity through the use of generator during the period of shortage. This system has the ability to deliver power for longer period and also has operating cost to be the cheapest. Advantages include high power capacity to about 3 GW. Drawbacks include a high capital cost for construction and environmental issues. Compressed air energy storage system. In this system, power from the grid is used to pump air into the underground geological formation until the air is at high pressure, and when the demand is high, this air stored undergoes a heating and expansion process inside a high and low pressure turbines and converted into electrical energy. Advantages include large energy capacity, little geographical dependency, and long lifespan, low cost per kilowatt power consumed. Its drawback is the difficulty in locating a specific geographical place for installation. Flywheel energy storage system. It is a rotating disk that can store or dissipate mechanical kinetic energy using rotatory inertia. In this, energy is stored in the angular momentum in a rotating mass. It is deployed in applications that require short duration with short discharge time in a range of 1 to 100 seconds. Advantages include low cost of maintenance, very high efficiency, high power density, and long lifetime. Drawbacks include low energy densities and very high losses due to friction.
Now we will move to another part of energy conversion, that is thermal based energy conversion.
Why do we need thermal energy waste conversion? Conventional thermal energy sources produces a lot of propulsion to environment, and low-grade heat from industrial-based geothermal activity and solar heating is wasted. So we need some mechanism to utilize this energy. Problem arises due to lack of energy storage capacity and the high cost semiconducting materials. Benefits of using thermal waste energy conversion are it is eco-friendly, cost-efficient, and it has high efficiency. Different mechanism of thermal electric conversion. In thermoelectrochemical cells, the electrochemical potentials of redox couples are temperature dependent and can be used directly to generate a output voltage at different temperatures. Also, there is a heat to current converting system on the base of the temperature dependent property of the charge supercapacitor's voltage at the charge state. A thermal waste conversion and thermally regenerative ammonia based battery trap. Thermal energy conversion is the ocean thermal energy conversion. It is a technology to generate electricity using as a heat source the thermal energy stored in the sea, in which a Rankine cycle makes the most of the temperature difference between surface and deep water.
In this part, we will explore the concept of multi-based energy sources and how they can help us build a more sustainable future. There are many benefits to using multi-based energy sources, including reduced greenhouse gas emission, reliability, energy independence, reduced environmental impact, economic growth, etc. There are many types of multi-based energy systems. Some of them are hybrid solar wind systems, combined heat and power system, microgrid solutions. Hybrid solar wind systems use solar panels and wind turbines, which can generate electricity under varying weather. Combined heat and power systems simultaneously produce electricity and useful heat, maximizing overall energy efficiency. Microgrid solutions integrate solar, wind, and battery storage to create localized and self-sufficient energy networks. While there are many benefits to using multi-based energy sources, there are some challenges, including intermittency, cost, transmission and distribution, policy and regulatory barriers. Some examples of successful multi-based energy projects are shown. Solar wind hybrid farm in Iowa, CHP in commercial buildings, microgrid powered neighborhood in Brooklyn, New York. Environmental impacts of multi-based energy sources are reduced carbon footprint, preservation of natural resources, long-term energy security.